Hello, welcome to my video on the fundamentals of the Java type system. I'm going to be just doing this, running through a demo of the basic types and some others. But first and foremost, I want to sort of highlight one sort of peculiarity of Java, and it's like really one of the most essential concepts about its type system is that the type system is divided in half. It has, or you could say it has kind of a schism to it. There's really two broad categories of types. There's primitives, and then there are classes. Now, this is really strange as far as programming languages go. it's there's not a lot of other languages that do this, but Java did this for the purposes of efficiency. So let's jump into this. So primitives are one type, and then we have classes. Let's say an objects is kind of the other type. A class really being a user-defined type in Java. An object being an instance or a particular one value of that type. But anyways, let's start with the primitives. And I'll just be running some code here as I go. Within this world of primitives, we have, well, a lot of them are just sort of number types. For example, everyone's favorite integer here. So I can set, here's an example of declaring an integer. Integer is a whole value, right? A whole number, rather. So, for example, 43, right? You can't do something like 43.3. I'm getting a type error there, right? Because integers are whole numbers, 1, 2, 3, 4, 5, and then it goes, 0, -1, -2, and so on, so forth in the other direction. Like I said, Java split up types for efficiency. So when we have an integer, the other thing we need to know is it's going to be 32 bits. So when we get to talking about classes and objects, well, these, values can be much larger than this. So this is why Java wants the ability to be able to, pack numbers into relatively small, efficient area. So since this is 32 bits, this means, and this is sort of a rule of thumb that I always remember that, well, there's a limit to how large or how small an integer can be. So it's basically from about -2 billion to +2 billion. So that's why I keep in mind, you can look up exactly what the value is, but I think it's more helpful to remember about. It's just like a little more than 2 billion. So when you're picking an appropriate data type to use, you can kind of keep that in your mind of, is it appropriate, is an integer appropriate, and a lot of times int is sort of the answer if we need these discrete numbers, so whole numbers, etc. So anyways, integer is probably not too surprising to anybody. Now there's, to address this sort of range of values, and for the sake of efficiency, there's different kinds of ints. So this is a departure, say, from like Python, right, where you have the int type, but say in that language, there's actually no bound besides your computer's memory on how big or small that number can be. Like I said, Java, everything's fixed. This is, for efficiency. This is also kind of relates back to the whole C family of languages, etc. But anyways, we have a different type of integer here called short. That's another one. Short foo. It's going to look the same when I initialize it. So Java knows that if I write 32, okay, that's a short in this case. A short is going to be 16 bits, which means it goes from about 32,000, I should say -32,000, to +32,000. this is just another helpful thing to sort of to remember. I think shorts are a bit of a special case. You really only use these, for if you really need to care about efficiency. Basically, if you have a lot of numbers in your program, you're dealing with massive arrays. Maybe they're millions of entries long or something. Maybe you're gonna start thinking about, well, maybe I could shave down the amount of memory I'm using if it's array of ins to array of short ins. Generally speaking, don't really see this come up a ton in practice. It's really just to kind of cut corners a little bit on memory. Really need it. What's used a little more commonly though is a long. So it's a long integer. And we have to use, maybe Java will figure this out, but the literal for it, you do a number plus a capital L at the end. This is going to be 64 bits. And I should put down, this is, what is that? That's going to be, sorry, mental math, just brain fart here. That's 4 bytes. That's 2 bytes. And this is 8 bytes. Right, so if each byte is 8 bits, right, so we have 8 times 8 gets 64, 4 times 8 up here to get 32, etc. Okay, great. Longs are used for, you kind of see these for like things like the system time, maybe like identifiers for like you have a database, a bunch of some bunch of objects you're tracking. You want to have a unique identifier for each one or something like this. If you worried about hitting that 2 billion limit, longs are from -9 I think quintillion. I'm not even gonna spell this right. Oh no, I got it. Look at that. Up to 9, I think it's quintillion. Huge value. Huge huge range there. So longs cover a massive span of numbers. Again, this I typically see this like unique identifiers, that kind of stuff is good value for it. But yeah, so this is a long integer. It just gives you more possible values. If you think you're gonna hit this sort of 2 billion limit, then you can bump it up to a long and cover a lot more. Notice there's a pattern here too, that just in the names here, int, short, and long, they all start with a lowercase letter. That's not an accident. That's gonna that's sort of a hint that you're dealing with a primitive type. So we'll see this trend continue. Next, let's move into more numbers. So if these were integer numbers here, our decimal numbers here are going to include a float, and we can do classic pi here. So this is also going to be 32 bits, which is 4 bytes. And oh, I forgot my little semicolon here, so I type this out. Float is a little bit different. So then when we're thinking about the range of what possible values can we pack into these 4 bytes, it's going to give us 7 digits of precision. So you can think like seven of these digits written out with accuracy. I'm going to say, and then plus or minus, this can be raised to 10 to the 7. Is that right? No. Excuse me. 10 to 38. So this gives us a wide range here of possible really small values, really large values, but there's only so many actual digits or places for number of representations. So if I start going out beyond 7, if I start going out too far here, actually some of those are going to be lost. What wonderful error am I getting here? See? The type system says, surprise, you don't have a float anymore, you have a double. So it's a natural segue here. Let's take off digits so it stops complaining at me. Oh, no. Just kidding. Forget that. You have to put an F to say it's a float. And will it complain at some point again? Okay, just scratch everything I just said previously. You can put all that there. It's not that smart. Okay. You have to use this F here to say it's a float, because by default, that would have been nice if it would have automatically detected there's too many digits, but anyways, the next one's a double. So it's double precision floating point number. This is the the more standard decimal number. So let me put some stars up here by the int, because that's the sort of default people typically use. For double, for decimal numbers, double is the default one, so it's 64 bits. That's 8 bytes, and that means it's going to have 15 digits of precision, plus or minus, says 10 raised to 308 in range, so you get a huge range of values there. So anyways, that's why doubles are typically preferred over the little stars by this one as sort of a default for a decimal number. So if we need a fraction, double just gives us, and why is double precision? Look at this, it's more than, it's 15 digits, which is more than double 7 digits. Okay, hence the name. So anyways, Java, all these number types, fixed length, that way it can just be memory efficient when it represents these inside the computer, versus the contrast, like a language like Python. It actually uses something, a class or an object under the covers, so everything's going to be larger. It's going to use a lot more space, which matters if you're basically in the realm of scientific computing. So if you're a large number of numbers, this really starts to add up quickly. Anyways, let's move along to, not classes, object yet. We have a few other miscellaneous types here. So another primitive type is everyone's favorite, the Boolean. So this can take, true or false. I'm stuck in the Python habit there as I switch context here, but it has to be lowercase t true or lowercase f false. So there's only 2 values. This will still be 8 bits though, or 1 byte, and that's sort of an artifact of how the computers in general ultimately address and access memory. It's typically at minimum a byte. There are, I'm not sure if Java is this optimization or if they consider putting it in, but sometimes certain languages will do like byte packing. So if you had like an array of Booleans or something like this, it might squish it all into 8 of them at a time into a single byte. Java, I don't think, cares that much about efficiency, so I'm just going to use 1 byte for a Boolean. And then another one we have is a character. Character is another primitive type. So if we just want a single letter, we use single quotes around it. And this since it's Unicode values, this should be 16 bits or 2 bytes involved there. Yeah, so this is again a departure from like a language like Python where there's just a string type and you just have maybe strings of a single length. In Java, it has an actual fundamental primitive type called a character. It can just be one letter. And this using 2 bytes here. Wanted to do that. Well, to support Unicode, this means non-Latin characters can also be represented, which is helpful for making programs that have internet support international users. Anyways, so this is sort of one half of the types system. I'll give some more examples of using operators with some of those types. Particularly looking at division, but let's just talk about the other half. So if these were primitives up here, maybe I should put little dashes up here. Hey, look at that style. Okay. Classes and objects. This is our other sort of realm in the Java type system, and this distinction will matter more later. Start building more sophisticated applications. We'll see this sort of distinction shows up a bit more, but you can just have something called an object. This is the root of this half of the type system. There's not a lot to this thing, just call it an object. It's just sort of this, ancestor of every other sort of class we're going to make or can be made in Java. A more sort of meaningful example of a class and object would be a string. So again, look at how both these types start with a capital letter. That's also not a mistake or coincidence. Yeah, so basically the classes always start with the capital letter, primitives start with the lowercase. IntelliJ, highlights them differently for us, which is convenient. But this will take some more sort of explanation, more videos, dive more and more into objects and classes. But this is a whole series of built-in types, also like string, that obviously have special support because of double quotes, right? So that's special syntax. But also user-defined types. So if you're gonna make a person class, a car class, a student, university, you can start thinking of all sorts of different things you might want to represent. In Java, what you do is you end up making a class for each one of those things. The other maybe simple, useful one would be scanner. So this is how you can do input and output in Java pretty easily. So typically to create, so if you look up here, to create like a number, like an integer or a long or a float, there's some we call literal to create a new particular value. So rather, float is a type, but a particular float, a actual number, right? We can just write it out like this and then put F at the end. So scanner is a type, but to make a particular one, and this is true for every object, well, except for strings. Let's go asterisk there. We use the new keyword. So to make a new one, so we're making a particular scanner here, and then I'm just going to give it system.in for now. So this could take command sort of console user input for basically a command line program. Great. So yeah, that's the two halves. There's a lot of more subtleties that come up um, with these two types, or this sort of schism in the type system, mostly when it comes to, well, one, there's the whole efficiency of this, all these things being packed into a few number of bytes. All these are going to be at least 8 bytes for a class, because these these are all by what we say by reference. So what happens here is this type string, really this whole, let's consider this whole variable. So string strfoo here. What it's actually holding is not the letters H, E, L, L, O. That's actually somewhere else. What this variable holds is just an address that points to hello. So this is like maybe a subtle distinction here that seems a bit abstract for now. I'll have sort of more videos on this later, more explanation of this later, but really, and that's what this new keyword sort of hinting at, is that when we create a new thing, a new object, or a new scanner, or a new string, or new instance of a class, it's not actually contained within this variable. Each on the left hand side, these are just a reference or like a pointer to it. So this thing's going to live in a different part of memory in our program. This is going to be kind of floating out there, and then this variable on the other side is going to be a pointer to it. So if I end up doing scanner, let's call it, creatively input2, and I say equals input, what's actually happening here is both, the reference is copied. So meaning both input 1 and input 2 are actually pointing at this thing. They're both pointing at that. Same thing if I did, strfoo 2, this, they're both going to be pointing at this same value. So there's only one string here, there's only one scanner here, even though there's two variables for both. Both those things are pointing at this particular value. Unlike if I were to do, double foo 2, and I said it is equal to double foo, this actually, copies the value. So now I have two. Oh, I said the twice. I don't know why I did that. It actually copies the value 3.14 and puts in the double foo 2. So now there's actually two numbers that exist. Unlike the class system down here, or if I do this assignment again, now there's two pointers or two references to the same thing. You could use sort of a metaphor of like street addresses. Now this is not exactly how street addresses and houses work, but you can imagine you could have a house and you could have one address for it, and then 1000 Maple Lane, and then you could say, oh, actually, you could slap a different address on it. Now they never do this in real life, but you could say, oh, it's actually 2000 Maple Lane, same house, or something like that. So it's sort of, this is more like like I said, a reference or a label or pointer. It's not the actual thing. Another maybe better metaphor would be just getting mail to a person. You could say, well, you could send it to their mailing address, which is their street address, or a PO box number, right? And basically the mail is going to end up with that same person. You can check his PO box, or you can check his his mailbox in front of his house. Both those sort of point to conceptually the same person. There's two different ways to get to that person through the mail. Same thing here. There's two different, in this case, there's two different ways to get to this single string that says hello. Okay, just a few more details here. Um, Let me just take all my lovely code here. I'm just gonna get rid of this, I think. Yeah. Um, so let's go back and let me just show you a few different operators, right? So if I have two different numbers here, I mean, and I'll just print out the results. Now, there's basically no one's surprised that, plus exists, right? You can add two numbers together. Surprise. If I run this, I don't know. Okay, it took far too long for that to happen, but okay, so you can add them together. Wonderful. You can subtract them. Run this. Great. Multiply. Great. All that's what you'd expect. Maybe other than maybe the star surprises you as a symbol for multiplication, but apart from that, not a big deal. Okay, let me change maybe the values here. Let's do 7 and 3. So now division. Division gets to be interesting. So if I did foo divided by bar, we have 7 divided by 3, right? Now, what does this slash mean? Again, in the world of programming, typically what you have is two different kinds of division. In Java, it's just going to correspond to these two different declared types. So if you're in the sort of integer world, what this division is going to mean is going to be integer division. So I run this, I'm going to get 2 out, right? Because, 7 divided by 3, in reality is going to be, 2.5, right? But integer doesn't have capacity for this fraction, so that just goes. So that's why we get down to just 2. So the remainder is just lost. First is, if we do this, now if we want the remainder, we're going to do 7 divided by, we can put mod 3 here, but really we're doing the division, and we're getting back to that, basically that 0.5. Let me run this. Or maybe I just totally messed up the math here. Yeah, it's just 1. Okay, never mind. Yeah, it's not 0.5, it's 0.3, right? Yeah, forget that. When I was up here, it's 7.3. So just forget my my inability to do mental math at the moment. Because we're dividing by 3, it's going to be thirds, not halves. I usually do this example divided by 2, but whatever. Okay, dividing by 3, I'm going to get a third left over, 1 over 3. So this ends up being 1, right? Which is really to say that's 1/3. That's the remainder. When we think about, division normally, you take 7 divided by 3, you're getting 2.3 remaining, 3 through 3 repeating. If we have an integer, in this case in the computer, we don't have the capacity to represent that decimal, so we just get, for division, we just get the quotient. For a mod here, we just get the remainder, which is a third. So it's basically the 1 over 3. Anyways, so if we change the types here, the outcome will change too, because now the meaning of this operator has changed. So no longer we're doing integer division, we're doing floating point division. We get thirds, so we're just gonna get 3, repeating on for almost forever there. We do still have mod. It's still going to give us that remainder, but if you notice, instead of 1, it's 1.0, so it comes back as a float. And it's the same for doubles. So within those broad categories of of types, we're fine. What happens if we mix and match? Let's do that. What do we think is going to happen here? Well, let's find out. Let's just give it a run. It's going to be, oh, it's still the floating point answer. So what happens is, because double is in some sense a more generic type, or like let's say the decimal numbers in general are more general type than the integer based numbers. We can just sort of convert the integer implicitly into a double and then perform the division. That's what's happening here. So bar gets basically converted into a double, and then division's carried out. So just know that when you sort of do this mixed mode of operations here, that is mixing mode, meaning mixing these two different types. We're particularly mixing doubles and ints, or floats and ints, or floats and shorts, etc. Between those two sort of camps of numbers, you're going to get this automatic conversion over into the decimal number. That's how Java works. So that's just an important thing to remember. If you want to do the conversion, let's just talk about, well, there's an implicit conversion happening here. What if you want to make it explicit? What if you want to do explicit conversion? So if you had BAS, we have it, 3.0. Let's kind of forget the division situation here. And now I want to assign BAS to bar. What's going to happen? Well, there's a type mismatch here, so you get this type error. Okay. How do you fix that in Java? You have to use something called casting. This says treat BAS as if it was an integer, and then whatever that value is going to be assigned to bar. And let's just print it off. What it should do is truncate. Let's do actually print line. Let's just run this. Yeah, we just get 3. So there's a truncation here of that decimal number down to a whole number. That's what happens here with this. It's called a cast, but it really converts this number, this floating point number, into an integer. So that's another important thing to know. You can, with relative safety, go the other way. So if I, let's say, forget that. If I, well, no. Let's change the order here and say, okay, bar is going to be 7, and then let's do this. You typically don't need to do this conversion like explicitly again. You could say, make this into a double. It makes it gray because it says it's redundant. Because again, the idea of a decimal number is more general than an integer or a whole number, so you can, with relative safety, convert it. When I say relative, because we just have to think about all those digits of precision if we're actually losing anything. But anyways, so there's that. So now let me just cover one other topic of conversion here. So let's just get rid of this in general. Let's just say we have a string. Where's my brain at today? But okay. Can't type either. That's great. So I have my string form of pi here. How would I make it into an actual double, right? Double pi here. That's a great pun. For each of those primitive types I mentioned, like float, double, integer, int, character. There's going to be this corresponding class for it that has static methods. You can really think just a function that are these sort of helpers out there for it. So for example, if I use capital D double, that's going to be referring to this class called double. So it's a sort of companion class. You see in Java that lang there. I can say what is it, parse double, and give it, oh, let me call it pi2 there, avoid that type error, of course, or that syntax error. So parse double will in fact convert that string, if it can, into an actual number type. So I'll print pi2 down here. Let's just give that a whirl. We see 3.14 here. To prove that it's actually a number, I can add 1 to it, let's say, so that we know it's not a string, and we say, hey, okay, that's 4.14. This is a good example too when I was talking about digits of precision. Notice we kind of run out there. We get to a little bit of fuzziness, right? Where do we? Maybe we can count. I don't know if maybe there's 15 there. 7, 8, 9, 10, 11, 12, 13, 14, 15. Wow. Okay, I was right on then. So you can see there was 15 digits there, and then on the 16th, we get this 1 shows up. Where does that come from? Well, basically everything after that 15th digit's more or less kind of a lie. So we start getting some goofiness there. So that's a numerical issue, we might call it. So that's why, when you can use integers, you don't have this sort of fuzzy number issue. Anyway, that's an aside. Doubles are a way to parse doubles from strings. If I want to parse, let's say an integer, I can do parseInt, and I can just give it 3 here. Great. As a string, it will convert it to an actual number, and then I can do math with it, print it out, etc., etc. Okay, I just see 3 down there, and again, I can prove to you that it's an actual number we can do arithmetic with. A is 4. Okay, so there's these companion classes. You just should know they're there. They're for converting, things like strings into actual doubles and ints. Basically numbers we can actually do arithmetic with. If you want to go the other way, say 3.14 up here. Well, let's do this. Let me change my example again. Here, let me delete this. So if we want to go the other way, and I have 3.14159. That's all I got memorized of pi. But let's say we want to go to a string. Probably a good way to do this is, I'll stir pi here. Is to use this. It's not quite a companion class because we can actually instantiate this one, but you can think it's sort of parallels it. We have string, and then we have some lovely static methods, i.e. functions we can do with this format, and we can use the kind of standard formatted placeholders here. So I'm going to make a string. I want it to be I'm basically going to take a number, a floating point number, and we're only going to keep 1 digit past the decimal. Let's throw this in here, and then let's print this out here at the end. Let me run this, and we just see 3.1 appear. So this is kind of how you would convert the other way from number into string. Now this gives us more options. There's a lot of implicit format conversion too. Like you can just take a string and say plus this number, and it will just convert that number, whether it's a double or whether it's an int, into a string for you, and then do concatenation. So there's a variety of ways to kind of get numbers into strings, but string.format is a good way to do this. If you want to combine these two operations, what we can do printf instead of printline, and then I can just put this sort of placeholder in there. I have to put a new line character on the end, so that does this down here, where after I printed, the cursor is actually on the next line. That's what the new line character does, is it advances the console to the next line down. Yeah, so I can basically combine these two lines of code into this line of code by just using printf. And if I just run this, we get the same output. And notice that it's on its own line, right? And there's an empty line afterwards. Yeah, so that's it for my explanation of just the sort of fundamental types in Java. Remember, just recapping, we got this sort of schism in the Java type system, right? Primitives, and we have classes. So those are the two halves. Primitives are there, basically for efficiency's sake, efficiency in terms of memory. We can pack, numbers into a relatively small footprint, versus classes on the other end, not as memory efficient, but they're really rich in terms of we can define new types, we can add a lot of behavior to them, we can add a lot of properties to them. There's a lot of extensibility there. So Java decided to sort of cut their type system in half into primitives on one side and classes on the other. And then there's all these kind of conversions back and forth. There's weird particulars like integer division and that sort of thing. And that's just a throwback contrast to I'm going to say integer division depends upon sort of declared types, right? So that's how Java knows. If I'm, dividing with pi here, it knows because this is a double which kind of division to perform. Unlike, say, Python, where there's a different operator, right? It's a single slash for floating point division versus double slash for integer division. But anyways, that's it. So there's these types, basic operators on these types, type systems cut in half, and then, yeah, that's about it. So thanks for listening.